Greetings everyone, my name is Rimon Mondal. I am going to present the paper PBVM-SP, a priority-based VM selection policy for VM consolidation in Green Cloud Computing. These are my co-authors. The topics for today's discussion are this: Introduction, Literature Survey, Proposed VM Selection Policy, how we have implemented it in a cloud sim, some performance evaluation, and conclusion. Cloud computing is basically a service-oriented architecture that provides services on pay-per-use basis. That means you have to pay for the amount of time and amount of resources you are using from the cloud infrastructure. Some uh, services like infrastructure as a service, platform as a service, software as a service, data as a service, storage as a service. All these services are provided by or served by large-scale heterogeneous data centers. Thousands of physical servers and IT resources are clustered together in those data centers, and these data centers are working constantly for 24/7. The main concern here is that these data centers actually requires enormous amount of data generated from fossil fuels, and that elevates the carbon footprint of the environment. If are to be understand this by the facts or surveys, uh, Liu et al. They have estimated that by the year 2030, the data center will contribute 720 million tons of carbon footprints to the environment. Also, Andre and Edler, they have also predicted that by the year 2025, the data center will lead the energy consumption with 33% of the total energy consumption by the ICT industry only. And according to their survey, also by 2025, the 4% of the Earth's total energy is going to be consumed by the data center itself. To tackle this kind of problems, we require a green cloud computing. Green cloud computing, in the heart of this green cloud computing, a green data center is there. This green data center is actually manages the energy very efficiently and also manages the e-waste very efficiently. In this green data center, everything has to be environment friendly, like green building, green electricity, green air conditioning, green air flowing. So everything has to be energy efficient and environment sustainable. There are different approaches that can be used for achieving green cloud computing. This includes some technical approaches, some non-technical approaches. In the non-technical approaches, we can use renewable energy sources or biopowered data centers. So renewable energy sources also has some negative impact on the environment, like those solar panels or those turbines, those air turbines, they also have some negative impact on the environment. So we are actually interested in the technical approaches. In the technical approaches, we have virtualization and VM consolidation, dynamic voltage frequency scaling, some different software designs that can be used to minimize and efficient use of energy consumption, energy, some thermal hour management techniques that can use to lower the temperature inside the data center. In virtualization and VM consolidation, VM consolidation is basically utilizing the live migration of VMs to transfer a VM among physical servers in order to improve the utilization of resources and energy efficiency in cloud computing. Live migration means migrating a VM from one host to another host without turning the VM off. The VM consolidation framework follows these 5 stages. Workload analysis, where the workload from the different cloud users are being analyzed, and according to those analysis, some VMs are being created. These VMs, the configuration of these VMs can be dynamically adjusted whenever required. Then follows the VM placement policy. In VM placement policy, different policies or different algorithms are used to allocate these VMs, these virtualized machines, to the physical machines or physical hosts. Then host monitoring and categorization. So after allocation, uh, after several times, so for our experiment we have considered 5 minutes, all hosts are being monitored and they are being categorized between overloaded host, underloaded host, and moderate loaded host. Overloaded hosts are those VMs that has reached their physical limit and cannot allocate more VMs, as well as dynamic provisioning for the VMs that are being allocated to those overloaded hosts are halted. Dynamic provisioning means some VMs can request more resources whenever they require. So for an overloaded host, if a VM requires more resource, it cannot allocate those resources. So some some migration is required, some VMs are need to be migrated. For those, VM selection policies are used. VM selection policies creates a migration pool from selecting overloaded some VMs from overloaded hosts. VM reallocation and shutdown phase reallocates all those VMs from migration pool and shut down the underloaded host to conserve the energy. Some existing policies include growth potential aware policy, GPA minimum migration time policy, maximum utilization, minimum size policy, minimum migration based on TESA. All these algorithms we have used for comparison or comparing with our existing policies. These algorithms, they are mostly based on the utilization, but our policy is based on the time they are being deprived. So we are going to come to that part. For our policy, we have analyzed a special metric called VM status history. This history is being recorded for all the VMs in a particular host in every 5-minute interval. This entry includes the timestamp, requested MIPS, allocated MIPS, and is in migration field. The timestamp is basically the current time. Requested MIPS means the last requested processing capability by the VM at that timestamp. Allocated MIPS means at that time how much allocated processing capability was allotted to that particular VM. And is in migration has two values, binary values, 1 or 0. If it is 1, that means the VM is in migration, that means you cannot consider that, and otherwise it is 0, that means the VM is not in migration state. So a VM selection policy is basically starts with a list of overloaded hosts and selects a VM from each overloaded hosts and creates a migration pool with all the selected VMs. In our proposed policy, we have analyzed the VM history and looking for the amount of time a VM is deprived. That means allocated processing capability is less than the requested processing capability. These VMs actually suffers from performance degradation because their request cannot be fulfilled by the overloaded host. The reason we have discussed already. The VM that suffers the longest time will be selected for migration. But we have a catch here that if a particular VM is in migration, that is not need to be considered, or if it has been migrated or it has the request has been fulfilled within the last 15 minutes, then these VMs are not going to considered for the selection. So this is the priority calculation phase. In this phase, the input is the VM, a single VM, and the priority of the VM is going to be calculated by analyzing its VM history. And the time difference, the amount of time their previously allocated processing capability is less than previously requested uh, processing capability is going to be the priority. And if within the last 15-minute frame they are being allocated with their requested MIPS, they are not going to be considered. So that is the priority is set to 0. In the VM selection policy, the input is overloaded hosts, a list of overloaded hosts, and for each of these hosts we are going to find out a particular VM that is going to be added to the migration list. So we are selecting a VM based on the priority. So we are calculating the priority of each VM for an overloaded host, and we are selecting the VM that has the maximum priority, and we are adding that to a list of VMs, and ultimately we are returning the list of VMs for reallocation. The changes we have made in the cloud sims are as follows. We have added a class power VM selection policy priority based, extending the org.cloudsim cloudbus.cloudsim.power.power VM selection policy. Inside that we have implemented our VM selection policy as public VM get VM to migrate power host. We have also updated the runner abstracted class, and we have included this particular code to call our proposed policy. And also we have for testing we have implemented test policy proposed policy. And this cloud sim is basically a simulation model, simulation toolkit proposed by professor simulation model. For any simulation model, real world workload traces are actually used for better understanding and better management and better consideration. So we have used real world workload traces generated by common project by Planet Lab. And the characteristics of those workloads are given here. 10 workloads of different days. These are basically the utilization history in 5 minutes of interval for 2 long months. And from these workloads, for the space constraint, we have selected 6 of the workloads for our evaluation. So as a simulation setup, we have used the basic default simulation setup that comes with the cloud sim itself, where we have two HP ProLiant machine powered with Xeon 30751 and another one is Xeon 3040. And for VMs, we have used 4 different VMs with different characteristics: micro instance, small instance, extra large instance, high CPU, high CPU, medium, and instance. As a evaluation matrices, we have considered 5 evaluation matrices. Energy consumption. Energy consumption is the total energy consumption of the cloud environment that needs to be minimized. SLATH is the percentage of time an active host is overloaded. That means how much time an active host is overloaded, the percentage of time from the overall time. It needs to be minimized. PDM is performance degradation due to migration. So whenever a VM is migrated from one host to another host, some performance is degraded. So that is PDM that needs to be minimized. SLAV is computed as SLATH multiplied by PDM, SLA violation. And ESV is a parameter that is the combination of energy consumption and SLAV. All these parameters were proposed by Rajkumar Bhuiya and their team. So from this particular graph, we can see that in terms of energy consumption, our proposed policy denoted by yellow. For all the experiments, our proposed policy is denoted by yellow color. So in yellow, for all the workloads, our proposed policy has the minimum energy consumption. Similarly, for SLATH, we can see for the proposed policy, our energy proposed policy for all the workloads, SLATH is actually high. So for a multi-objective problem, it is not possible to optimize all the parameters. So here we have actually failed. For PDM, our proposed policy is actually outperforming the existing ones. As we can see here, the yellow color represents the PDM. For SLA violation also, that is a combination of PDM and SLATH, our proposed policy outperforms the existing one for all the workloads. And for ESP parameter also, our proposed policy is actually outperforming the existing ones. In the conclusion, we can say that the problem of environment sustainability and carbon footprints is actually very much important in today's era, and we have analyzed this problem for different data centers, and we have proposed a VM selection policy that actually helps in reducing the energy consumption very significantly while maintaining the quality of service of the system intact. Also, in the future, we might like to explore the VM placement policies and physical monitoring system for better and efficient solutions. The resources we have used for preparing these documents are as follows. Thank you, everyone.